Diodes come in a variety of sizes and shapes for a number of different applications. We've already mentioned standard or signal diodes and light-emitting diodes. But there are also Zener diodes. There are laser diodes that emit a coherent laser light when in the conducting mode. There are photodiodes that are photosensitive and conduct when in the presence of light. So rather than a voltage across them causing them to conduct, a light shining on them causes them to conduct. There are high voltage and high power diodes, but in general all different diodes serve the basic function of allowing current to flow in only one direction, with a voltage controlling them. In this video, we'll demonstrate how we analyze diode circuits using either the ideal model or the constant voltage drop model of the diode. To do so, we're going to look at a number of common applications. First of all, relatively recently, within the last few years, LEDs have started replacing incandescent and fluorescent lights. In a common or standard base type light, instead of an incandescent filament, they have a constellation of LEDs. The LED is a much more efficient lighting source. It turns out that you can get the same amount of light out of a 6 to 10 watt LED as you would get out of a 60 watt incandescent light. Let's say it differently. A 60 watt incandescent light bulb gives off a certain amount of light, but it also has an awful lot of heat associated with it. That heat is an inefficiency of an incandescent light. So a 60 watt light bulb gives off a certain amount of light. Replace that with an LED, it will use about 6 to 10 watts of light, so approximately 1/10 as much power. The LED is much more efficient and doesn't get nearly as hot. And if they're manufactured correctly, the LED light bulb should outlast the incandescent or the compact fluorescent light bulbs also. You've also seen applications where headlamps and tail lights have been replaced with LEDs. They tend to be a brighter, crisper light, and again, more efficient and should last longer. And then finally, one application for illumination is the traffic control lights, which for the same reasons of efficiency and durability are replacing the traditional incandescent light globes. Okay, let's take a look at our first circuit here. This is known as a half-wave rectifier. This circuit takes an input signal that is going both positive and negative and effectively lops off the negative lobe of an AC signal, leaving only the positive lobes. Let's see how this might work. Here we have the input. It has both positive and negative lobes. When the input voltage is positive, the diode has a positive or a forward bias and will conduct. If we use the ideal diode model, we would then model this diode as with no voltage drop across it, and we would see the full input voltage across this resistor as long as the voltage is positive. When the voltage goes negative, this voltage here will be less than this voltage on this side of the diode. There's a reverse bias to the diode won't conduct. If there's no conduction, that means there's no current going through the resistor, and since the voltage across the resistor is equal to the resistance times the current, there will be no voltage showing across here during the negative swing of the source. So during the negative swing of the source, that negative is effectively lopped off, and at the output we have only positive voltages present. Now, if instead of using the ideal diode model we use the constant voltage drop model, let's just say that there's a 7/10 of a volt drop across that diode. In other words, the input voltage has got to get up to 7/10 of a volt before this diode starts to conduct. So the input voltage needs to get up to, say, 7/10 of a volt, and then as it conducts, it will continue to conduct as long as the voltage is greater than 7/10 of a volt. At the point that it drops below the 7/10 of a volt, the diode stops conducting. So the constant voltage is going to be closer to what you're going to observe in the lab when we build this up, and the output voltage is going to be about 7/10 of a volt less than the input voltage, and we won't even see that output voltage until the input voltage gets up to the 7/10 of a volt. This next circuit is known as a peak detector or a sampler. In this circuit, we replace the resistor with a capacitor. During the positive part of the cycle, once again assuming an ideal diode model, there will be no voltage drop across here, and whatever the input voltage is will show itself on the capacitor, and the capacitor will charge up to that voltage. The capacitor will just track the input voltage during the first half cycle. And it will charge up to a voltage equal to the peak voltage of the input, whatever that peak is. Now, as the voltage here starts to drop, we've got V peak here, something less than V peak. The diode is going to be reverse biased, and the diode will not conduct. So effectively, the capacitor is left with an open circuit here. The capacitor cannot discharge, and thus it holds that voltage until a higher voltage comes along. So if you've got a voltage that's varying and you're wanting to detect what is the peak voltage that we've seen, this little circuit right here will do it. The capacitor will charge up to and hold that voltage. This is also part of one critical part to a circuit that performs analog to digital conversion, where it takes an analog signal and converts it into a digital signal. This circuit here will sample the analog signal and then hold it while the digital number is calculated. Now, once again, if we allow for a constant voltage drop of, say, 0.7 of a volt, then this will track, as we've talked about before, but it'll only get up to 0.7 of a volt less than V peak, and it won't start tracking until you get a 0.7 of a volt drop. So it'll come up and then sample and hold at that 0.7 of a volt less than the peak. This next circuit is known as a DC restorer or a clamped capacitor. You'll notice in this circuit that we have simply reversed the positions of the diode and the capacitor. Now, in this circuit, think about what's happening. As long as the voltage is positive, no current flows. But as the voltage starts to go negative, we now have a reverse bias on this, and the diode will allow current to go. Again, first of all, assuming an ideal diode model with zero voltage across it, this capacitor will charge and will follow the voltage, looking at the capacitor, not the output voltage, but looking at the capacitor. The capacitor is going to charge up until it gets to, well, it will follow this peak voltage. And as long as it's continuing in this negative part, the capacitor is charging up. Now, as the input starts to go positive again, the diode will not be conducting because of the bias. But this capacitor will still have the positive to negative voltage on it, and it will have charged up to plus to minus V peak volts. Now what happens? The voltage right here, which is the voltage across the diode, is going to be always positive, so the diode won't be conducting, but it will hold the voltage at whatever this input voltage is. We go minus to plus, so plus V peak. In other words, the voltage here, the output voltage, is going to be whatever the input voltage is plus V peak. The input voltage is this. The peak value in the graph we have here is showing it at 5 volts. The capacitor would charge up plus to minus 5 volts and add 5 volts to the input signal at the output. So the output then is simply the input with a 5 volt DC offset to it. You'll notice that the output then would never go negative. If we were to allow for a 0.7 of a volt drop, and you'll see this in the lab, this is going to be something less than a 5 volt. In fact, it'll be 0.7 of a volt less than a 5 volt offset, and it will be something like that. Alrighty. This signal here is known as a voltage doubler. Let's look at what it does first and then see if we can figure out how it does it. If you have a signal coming in that's oscillating between plus or minus 10 volts, The output of this signal after a couple of oscillations will be 2 times the peak voltage. So for our input signal here, having a 10-volt peak, after a couple of oscillations, the output will be 2 times 10, or 20 volts, DC. It effectively takes the peak value, doubles it, and holds it. Let's look at the circuit and see how this might be. You'll notice that this circuit has 2 parts. This first part is the same circuit that we saw as the DC restorer, or this first part adds a DC component. The second part of this circuit is the sampler. So, this second part is basically following whatever this first part is doing and charging this capacitor to whatever this voltage here gets to be, and then holds it. This part here we call the sampler, or we also call it the peak detector. Detector. The voltage here is oscillating. Here's our input voltage. Here at this point, it's oscillating with that DC component added in, and the second part of it peaks or samples the peak and holds the peak. So the output here is going to be a constant, at least after the first couple of cycles. The output here is going to be a constant equal to 2 times the peak voltage coming in.